Welcome back to WAEC class. I remain Engineer Streven, and today we'll be talking about capacitors. What are capacitors? Capacitors are devices that are used for storing electric charges, and they can deliver these charges for a short period of time. Capacitors are of various types, but the most common one under the syllabus, under the scope of WAEC and JAMB exams, is a parallel plate capacitor. Just as the name implies, parallel plates, which means that the plates are parallel to each other, and the plates are metallic, and there's always a distance between the plates. If a capacitor is a device for storing charges, then the ability for the capacitors to store charges is its capacitance. However, this definition I just gave is a layman's definition, that the capacitance of a capacitor is the ability of a capacitor to store charges. Mathematically, the capacitance of a capacitor C is equal to the charge stored at either of these plates divided by the potential difference between the plates. This is how a physicist sees the capacitance of a capacitor. Is charge divided by potential difference. And the unit of capacitance is measured in farad. Now let me explain what I mean by charge divided by potential difference. The charge here is the charge stored at either of the plates. So here can be 20 coulomb, or let's just say here can be 2 coulomb, and here can be 2 coulomb. But the signs will not be the same. This will be positive, this will be negative. We're only picking one of them. Now, it means therefore that one of the plates of the capacitor will be positively charged and the other plates will be negatively charged. I'm connecting the capacitor to a cell or to a battery, which of course is charging the capacitor. Now, there are factors that can affect the capacitance of a capacitor, and I'm going to be looking at them right now. One of the factors that affect capacitance of a capacitor is the area of plates. And I can say that capacitance of a capacitor is directly proportional to the area of the plate. What this means is, if the area of the plate, this plate is very large, the capacitance will be large. And the area of the plate is small, then the capacitance will be small. So capacitance is directly proportional to the area of the plate. Another factor that affects capacitance of a capacitor is the distance between the plates, the distance between these plates. And this is how it affects it. Capacitance of a capacitor is inversely proportional to the distance between the plates, which simply means that the larger the distance between the plates, the smaller the capacitance, and vice versa. Another factor that can affect the capacitance of a capacitor, number 3, is the presence of a dielectric material. Now, simply put, a dielectric material is basically an insulator. So I can have a capacitor in which there is a gap. Remember, I told you that these plates do not have contact. So there's a gap between these plates. This gap can just be strictly vacuum or an air gap. Or I can decide to bring this plate extremely close to each other. If it's extremely close, there's a risk of the plate touching. So I can insert an insulator between the plates. That insulator can be plastic, can be glass, can be anything that is an insulator. Even some liquids can be used. So I can insert something in between the plates, and that stuff I've placed in between the plate is known as a dielectric material. What does dielectric material do to the capacitance of the capacitor? Dielectric material always increases the capacitance of the capacitor. So a capacitor with a dielectric material has a higher capacitance than the capacitor without a dielectric material, because of course I can bring the plates very close to each other and avoid contact. From this factor 1 and factor 2, I can write a new equation of the capacitance of a capacitor, and this is how the equation will look like. I can join these two together and say that the capacitance is directly proportional to area of plates and inversely proportional to the distance between the plates. Introducing a constant, I will say capacitance is equal to permittivity of free space A divided by D. Now recall that A is the area of the plates and D is the distance between the plates. If this E naught is the permittivity of free space, that is when there is free space or there is air gap or there is vacuum between the plates. But it's not all the time that there will be vacuum between the plates, because we just realized that there are times whereby they can place an insulator between the plates. So if they place an insulator between the plates, then it's no longer the E naught, but rather to be EM. So if there's an insulator between the plate, or if there's a dielectric material between the plates, I'm going to have C is equals to EM A over D. So these are the two formulas I can write. But look at this. This E naught here is permittivity of free space. This one is the permittivity of the material, the permittivity of the dielectric material I'm using, depending on the question that you are asked. There is something called relative permittivity. And another name for relative permittivity is dielectric constant. So if they do not call it relative permittivity, they can also call it dielectric constant. And relative permittivity is equals to the permittivity of the dielectric material, the permittivity of the medium, divided by the permittivity of free space. And in most questions, if they want to ask at all, they will give you the relative permittivity and they will give you the permittivity of free space, and then they will say that the dielectric material is inserted between the plates. And if I'm going to use anything that looks like this, I'm going to be using this one. But this one was not given. If I give you ER, relative permittivity, and I give you E naught, permittivity of free space, I can always make this one subject to a formula. And if I do that, I will have EM to be equals to ER E naught. And then I can put it in place of EM. So this will not, putting ER E naught in place of EM would seem as though it's a new equation, but basically it's not. It's just, I'm just getting it from this old stuff here. Now that we now understand the factors that affect the capacitance of a capacitor, we have looked at what a capacitor is. The next thing we need to look at is the work done in storing charges in a capacitor, or the energy stored in a capacitor. And after that, we are going to take questions. Alright, so now we are going to look at the energy stored in a capacitor, or the work done in charging a capacitor. The work done in charging a capacitor can be given by this equation, W is equal to 1 over 2 CV squared. And then this is all there is to the work done in charging a capacitor. I know you may not agree with this statement. Perhaps you have read other textbooks and you are seeing like 3 equations. I will tell you today that there's only just one equation. Other equations are derivative of this equation, and this is why I said so. We just said in the previous class that the capacitance of the capacitor is equal to charge divided by the potential difference. Let me make this charge capital letter Q. It does not even matter. But let's make it capital letter Q. Now, we know that W is equal to 1 over 2 CV squared. There are some questions whereby they will not give you C. Maybe they want you to find W, the work done in charging a capacitor, or energy stored in a capacitor. They want you to find W. They did not give you C, but they gave you V. You know that in order for you to find W, you need C and V. But they will not give you C, they gave you V and they gave you charge. I can come here and find my C. Once I find C, I can plug it back into this place and I'll get my answer. Then the person will just say, why stress myself? I can just say anywhere I see C, I put Q over V. If I do that, I'll be having W is equal to 1 over 2. Yes, C. But instead of putting this C, I'll put Q over V. And if I do that, I'm going to have Q over V, then times, of course, V squared. This V squared that's here. If I open this bracket, of course, this one takes out one of these, and I'm going to have W is equals to 1 over 2 QV. And then they will say that this is a new equation. This is not really a new equation. A student does not need to memorize this and memorize this and memorize the third one I can even form from this. All you need to know is to know the work done in charging a capacitor. And you already know what the capacitance of the capacitor is. If you know these two things, then you are ready for any question that they can ask around here. You do not need to sit down and memorize this third one, this second one. I can even give you a third one. You can get a third one from making the charge subject to formula, or making V rather subject to formula. You can do it like, if I make V subject to formula and plug it into this, I'll get another equation. But you do not need those 3 equations. Just know that all you need to know about the work done in charging a capacitor is this. The next thing that we'll look at is the arrangement of capacitors. And of course, there are 2 ways we can arrange capacitors, either in series or in parallel. Once we look at that, then we'll take further questions. Welcome back to class. And right now, we are going to be discussing the arrangement of capacitors. Just like I earlier said, there are two ways capacitors can be arranged. They can be arranged in series or they can be arranged in what? Parallel. This is series arrangement, where the terminals of the capacitors are connected end to end. From one positive to the negative, from the negative to the positive, like that, like that, like that. So this is a capacitor. And by the way, these are the symbols of capacitors. See that these lines are straight. Do not mistake it for this. This one will be a cell, but this is a capacitor. The lines are equal. Now, this is three capacitors arranged in series. It can be three or more capacitors arranged in series. Down here, we have two arranged in series. They can ask you to find the equivalent capacitance. What I mean is the capacitance of the combination. Once I combine them, I'll have an effect for combining the three of them. So that's your equivalent capacitance or the resultant capacitance or the total capacitance, depending on what term they want to use. Now, for capacitors arranged in series, the total capacitance basically is 1 over C total will be equal to 1 over C1 plus 1 over C2 plus 1 over C3. If they were to be 4 plus 1 over C4. So this is my C total, which is the total capacitance or the equivalent capacitance or the resultant capacitance. Once I add these guys up mathematically with the values we're giving me, then I'll make this C T subject to a formula, then I'll get my answer. I can do the same for this guy, but once they are two, there's no need of doing it like this. If I do it like this, I'll still get answers. But to be faster, once there are two and two capacitors connected in series, then I'll just easily use product over sum. And I'll just say C total is equals to C1 C2 over C1 plus C2. I don't need to do the reciprocal again. So if, for example, maybe I was having here to be, this C1 was 2 farad. By the way, the unit of capacitance is in farad. Let's say this one was 2 farad, for example, or microfarad. Let's just use farad. This is 4 farad, for example. And let's say this is 8 farad, for example. All of this, I want to arrange them in series. I will apply this same approach I just gave here. And it will be 1 over C total, which I'm looking for. I'm looking for the equivalent capacitance. Will now be equal to 1 over 2 plus 1 over 4 plus 1 over 8. Now, I'm looking for C total. So the first thing I'll do is find the LCM of 2, 4, and 8. And obviously the LCM of 2, 4, and 8 is 8. So that the 1 over C total is equal to over 8. 2 into 8 will give me 4. 4 times 1 is 4 plus 4 into 8 will give me 2. 2 times 1 is 2 plus 8 into 8 will give me 1. 1 times 1 is 1. I will add this up. I will now have 1 over C total is equals to, if I add up all of these numbers, I will get 7 up there divided by 8. This is why I wanted to explain this question this way. Because you see, what I'm looking for is C total, the equivalent capacitance. But what I have here is 1 over C total. So I have to turn this around. I have to take the reciprocal. And if I do that, I'm going to have C total is equals to 7, is equals to 8, excuse me, is equals to 8 over 7 farad. I can leave my answer in decimal point if the question demands so. So that's for that. But when it comes to them being arranged in two capacitors arranged in series, I don't need to do this. I will still get the same answer if I use this. So if, for example, come down to this part where we have C1 and C2. Let's say this one were to be 4, for example, and let's say this one were to be 3, for example. 4 farad, 3 farad. For this down part now, if I wanted to find the equivalent capacitance, I could use the same approach, but it would be waste of time. Since there are just 2 and 2 capacitors arranged in series, then I'll just do product over sum straight. Then I'll just say C total will be equals to product, which is 4 and 3. 4 times 3 over sum, which is 4 plus 3. C total will simply give me 4 times 3 is 12 over 4 plus 3 is 7. I'll get 12 over 7. Even if I wanted to do 1 over C total is equals to 1 over C1 plus 1 over C2, I will end up having the same answer here. So I don't need this one when they are arranged in series and it's just only 2. And notice what I did here when using the formula for product over sum. All I did was I found C total and I did not take the reciprocal of it. That is it when they are arranged in series. And then another thing I need you to know again, if they are arranged in series, is the PD across each and every one of them will be different. Let's say I have the total potential difference from this end to this end. And let's say that total potential difference from this end to this end is V total. But the potential difference across each and every one of them will be different. And there are questions, of course, JAMB have tried it in the past, whereby they will want you to find potential difference across each and every one of them. This is the formula you would use. For the potential difference across V1, it will be equal to C total V total over C1. For the potential difference across V2, it will be equal to C total V total over C2. And for the potential difference across V3, it will be equal to C total V total over C3. C total is our capacitance, total capacitance of everything combined, and C3 is for this guy in particular. V total is the potential difference across everything, all in total. The same thing goes for this one, where C1 is now for this first capacitor, this particular capacitor, and where C2 is now for this particular capacitor. Now let's move ahead to parallel arrangements. To get the equivalent capacitance in parallel arrangement is extremely simple. All you just need to do is to add up everything. So in this case, I have C1, C2, and C3. I want to add them up. If I'm asked to find the total capacitance or the equivalent capacitance or the capacitance of the combination, depending on what language I want to use, just know that it's going to be equal to C1 plus C2 plus C3. I'm just adding. If there were to be 4 arranged in parallel plus C4. So in parallel, you just add them up. Now, what is interesting here is, if they are arranged in parallel, let's say the PD across this end to this end is VT, or is V. They will all share the same potential difference across this end if they are arranged in parallel. But if they are arranged in series, they will not share the same potential difference. The potential difference across each of them will be different. So that is all for the arrangement of capacitors. However, JAMB would not just give you the question straightforward like this. There are some kind of diagrams whereby it could be a combination of series and parallel. So you need to identify which is series, and you need to be able to identify which of them are in parallel inside that arrangement. Another quick note you should take note of, another quick note you should have is, in series, there's no junction between them. I can say that this guy and this guy are in series because there's no junction. If a current was to be made to flow through, the current that will enter this will come out of this and still enter this because there's no junction, there's no branching. But if you come to this, if I make a current flow like this, once the current gets here, some parts will go up, some will come here, and some will come here. So you see that there is branching. Whenever there is branching, I will know that these guys are in what? Parallel. So this is an additional note. In our next class, we'll take further questions. Question number 1 on capacitors. Now, question here, a parallel plate capacitor has a common plate area of 5 times 10 to the power 4 meters squared and plate separation of 2 times 10 to the power minus 3 meters. Assuming free space, what is the capacitance? So they say assuming free space. What formula am I going to use in this question? Since I'm giving me area and distance, I know its capacitance is going to be equal to E naught A over D. Now I'm using E naught, not EN. Why? Because the question says assume free space between them. So there's free space between the plates, so it's E naught, permittivity of free space. So I'll go ahead and say permittivity of free space has a value, and that's 8.85 times 10 to the power minus 12. So I will say 8.85 times 10 to the power minus 12. That's the value of E naught. Then the area is 2 times 10 to the power minus 3 divided by the distance. Sorry, the area is 5 times 10 to the power 4 divided by the distance, which is 2 times 10 to the power minus 3. We can just approximate this value to 9. Most times, JAMB will approximate this value to 9 if they give you. So we can approximate it to 9 so that we have 9 times 10 raised power minus 12 times 5 times 10 raised power 4 divided by 2 times 10 raised power minus 3. Leaving all the 10s first, let's work on the numbers. 9 times 5 will give me 45. Of course, times 10. Let's pick our 10. I have 10 here. I have 10 here. I'll pick one. That's the 10. Raised power minus 12 times 10 raised power 4. I will add up the power. Minus 12 plus 4 should give me minus 8. All divided by 2 times 10 raised power minus 3. Now, we can do this division. We can say 2 into 4 will give me 2. 2 into 5 will give me 2. Remaining 1.5. So I'll get 2.5 times 10 raised power. This minus 8 and this minus 3. So the raised power minus 8 minus 3. That will be 2.5 times 10 raised power minus 8. Minus times minus is plus 3. And minus 8 plus 3 will give me minus 5. So I'll have 2.5 times 10 raised power minus 5. So to make it look like standard form more, I'll move this decimal point forward once. And that will be 2.25 times 10 raised power. If I move the decimal point forward, I'm going to be adding 1. If I'm moving it backward, I'm going to be subtracting 1. So I'm moving forward once. That will be adding 1 to minus 5. That will be minus 4. Raised power minus 4. So we're looking for capacitance, which is in farad. That will be our answer. 2.25 times 10 raised power 5 farad. Let's take question number 2. All right, so this is question number 2 on capacitors. Now, in this question, they gave us this diagram, and they said that the equivalent capacitance for the circuit shown above is, that was the question, is, we are looking for the equivalent capacitance. Now, you know, I told us previously that JAMB will not just go straight to give us those kind of diagrams I was showing you, series straight and parallel straight. No, they will make it look complicated. And such is this. So how will I answer a question like this? The key to answering questions like this is to take them in loops first. That means I have to work on this one first and combine them. When looking at this, I will know that these two are in parallel. Why would I say it's in parallel? The one I told you were in parallel previously was something like this. I would say that they were in parallel because the current that will come here will split and there is a junction. I can also say these are in parallel because if the current is coming like this, it will split. Some will go here, some will go here. So these are in parallel and I can combine them. If I combine these guys that are in parallel, how will I combine them? I will add them up. Because in parallel for capacitors, I add up. So if I add this guy up, I'm going to have something like this. Now, this plus this will give me 4. 1 plus 3 will give me 4. 4 microfarad. This is 4 microfarad. This is 2 microfarad. And then this is 2 microfarad. This one, everything here are now in series. How do I know that they are now in series? Because the current is going to flow through this place. The same current that will come out from here, we have to enter here, come out from here, and we have to enter here. There is no junction from this point to this point. So everything is now in series. Now look at it. It's not drawn straight like this. Just like I showed you earlier, it was not drawn straight. It was bent like this. But I know that they are in series because no junction from this end to this end. So these are in series. These are in parallel. Now, since there are more than 2 in series, I cannot just do product over sum. I told you that I will do product over sum if there are just 2 in series. Now, more than 2 in series, I will have to use that 1 over C total is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Now, if I do that, I will have 1 over C total, which I'm looking for, will now be equal to 1 over 2 plus 1 over 4 plus 1 over 2. The LCM of 2, 4, 2 is 4. So this will give me 4, of course. 2 into 4 is 2. Times 1, 2. Plus 4 into 4 is 1. Times 1, 1. Plus 2 into 4 is 2. Times that 1 is 2. Everything will give me 5 over 4. But I'm not going to stop here because this is 1 over C total. Let me just write it down here so that somebody will not be confused. I will have 1 over C total is equals to this 3 plus 2, that is 5. So I'll have 5 over 4. Then I'm looking for C total, not 1 over C total. I have to turn this around. And if I do that, I'm going to have C total is equal to 4 over 5. This will give me, now check the options. The options are left in decimals. So I don't have to leave it in fraction. So 5 into 4 divided by 5 will give me 0.8 microfarad. Although the unit of SI unit of capacitance is in farad, not in microfarad. But I'm not going to bother myself to convert because the options were left in microfarad. So this is my final answer. And that would be option what? Option C.